Hi, everyone. My name is Sunho Hong. I am a professor emeritus at Hanyang University, Korea, and a fellow of Nestfield Company. I am happy to give my keynote speech Asset Administration Shell Digital Twin for Smart Manufacturing at this IEEE SDPC conference. This figure shows the smart manufacturing of the future. In the green boxes, humans dialogue with each other. In the white boxes, machines dialogue with humans and even other machines. In the blue box in the top right corner, a manager gives new orders to humans and machines. The key message of this picture is that the factory of the future will give machines the ability to communicate, thereby ensuring process autonomy. This figure is the conceptual diagram of autonomy in smart manufacturing. In Industry 1.0, two people meet together to accomplish a task. Following is their dialogue. Do you speak English? Yes, I do. Who are you? I am a drill man. What is your capability? I can drill holes with the following quality. Fine. Drill me a hole. Yes. Done. But, in Industry 4.0, two machines talk with each other. Do you speak Industry 4.0? Yes, I do. Who are you? I am a drilling machine. What is your capability? I can drill holes with the following quality. Fine. Drill me a hole. Yes. Done. So, conversation among machines is the most important issue to realize autonomy in smart manufacturing or Industry 4.0. This machine-to-machine dialogue can be realized with the technology of the digital twin. Then, what is a digital twin? When we digitally represent a thing as it is the digital twin of that thing. As shown in the figure, if a factory is digitally expressed as it is, it becomes the digital twin of the factory. Factory? It's too complicated. Let's make a digital twin with a straightforward asset. Here is a mug with coffee. Shall we create a digital twin of this thing named coffee mug? If you create a digital representation of a coffee mug by file, it becomes the digital twin. This digital twin will include the color, shape, and size of the mug, as well as the composition and temperature of the coffee. Now, Korea's Chulsu makes a digital twin of a coffee mug. Michael from Germany also makes a digital twin. Also, American Anna makes a digital twin of the same coffee mug. However, all of these digital twins will be represented in different forms. To compensate for this, you can give a standard template and ask them to fill in the blanks. However, still there exist some problems. Chulsu, Michael, and Anna fill in the blanks with Korean, German, and English, respectively. Also, the unit system they use will be different. To supplement this, standard technology called CDD or a class, which standardizes the method of expressing the properties of things, is adopted. Now, anyone in the world can write and understand the digital twin of the coffee mug has been completed. This is the principle of the standardized digital twin. And Asset Administration Shell is the digital twin that is invented for smart manufacturing. Again, Asset Administration Shell is the standardized digital twin technology designed for the smart manufacturing application. In other words, the Asset Administration Shell digitally expresses not only the characteristics of all assets or things in the factory but also their behavior. As shown in the figure, hardware, such as machines, terminal blocks, and electrical access, and even software can have their own asset administration shell. These asset administration shells allow assets to communicate with each other. All assets in a plant can have asset administration shell from the part level to the machine made up of parts. The process that is a collection of machines, and the factory itself, which includes multiple processes. Asset administration shell has common submodels that all asset administration shell have in common, and domain-specific submodels that include specific information about each asset. Common submodels are composed of submodels that can contain information such as identification, communication, engineering, configuration, life cycle status of the asset, etc. Domain-specific submodels contain information about the data and functions of specific assets such as drilling machines, milling machines, and robots. Many people say that the key technologies of smart manufacturing are cyber-physical system and Internet of Things. Cyber-physical system refers to the digital transformation of physical assets, and the aforementioned digital twin and asset administration shell fall into his category. All assets in the factory have asset administration shell, and these asset administration shells can be connected through the Internet of Things, enabling communication of all factory assets. Even before smart manufacturing in the Fourth Industrial Revolution, the concept of a digital twin existed. The digital twin in the Third Industrial Revolution was mainly to monitor the process in real time through a dashboard, or manage the state of the process through simulation. And the simplex data flow was the primary concern. However, the big difference is that the digital twin of the Fourth Industrial Revolution is given the functionality of interaction between assets through the duplex data flow. Many people understand asset administration shell as a problematic technology. The reason is that the new concept of the digital twin is not readily embraced. However, it is not difficult to apply asset administration shell technology in practice in factories. Anyone can develop an asset administration shell model of their asset using the AASX Package Explorer tool shown, which can be downloadable from the Internet. In other words, anyone can implement the asset administration shell model as long as they understand how to use the AASX Package Explorer tool. Here are a few examples of how future manufacturing systems can evolve by adopting asset administration shell technology. First is the use case for order-controlled production. For example, suppose a product from a factory is popular in the market. Naturally, the producer will want to request the production of the product from another factory to increase the shipment of the product. With the current technology of the Third Industrial Revolution, the human producer has to negotiate with other human factory owners to carry out these tasks, which will take a lot of time and money. In the worst case, the product may lose its appeal in the market at the end of the negotiation. In the smart manufacturing technology of the Fourth Industrial Revolution, direct communication between factories with asset administration shell becomes possible, and optimal negotiations can be made quickly with artificial intelligence technology. A subsequent use case is an adaptable factory. An example of an adaptable factory is plug and produce. As explained in the previous slide, producing a new product in an existing factory requires changing the machines. In the existing third industrial revolution technology, the operator has to redesign the process with a new machine and create a new process line, which is time-consuming and expensive. In smart manufacturing of the fourth industrial revolution, direct communication between machines is possible with asset administration shell, which means exchanging functionality and data between machines becomes possible. Thus, by removing the old machine and plugging in the new machine can autonomously interact with existing machines in the process. The introduction of artificial intelligence technology here will expedite the implementation of autonomous factories without workers. Asset administration shell can be installed not only on the factory's manufacturing-related assets but also on the products produced in the factory. All information generated during the duration of using asset administration shell-equipped products by consumers can be fed back to the factory. And this information can be utilized when launching new products. For example, when a car is released from an automobile factory, all information generated while operating a vehicle may be fed back to the automobile factory and reflected in the launch of a new model. A worker handles many assets in a factory. In most cases, these assets are supplied by different vendors, and workers have to learn manuals for each asset from time to time. If all the assets in the factory can be connected through a standardized interface called Industry 4.0, through asset administration shell, the work efficiency of the workers can be greatly improved. In the third industrial revolution, products are produced through complex processes such as conceptual design, detailed design, part production, assembly, prototype production, testing, evaluation, design revision, parts revision, prototype revision, etc. Suppose we use the asset administration shell technology. In that case, we can virtually design and manufacture parts that go into products through asset administration shell. Also, we can assemble virtual parts to test and evaluate virtual prototypes with a computer. Then, an actual prototype is produced after verification of the virtual product is completed. Now, we can significantly reduce the cost of trial and error required for production. We can expand this virtual production concept through the entire value chain of the manufacturing process. So far, I have compared the differences between the present third and fourth industrial revolution technology to come in the future through a few examples. The examples presented here introduce only a tiny part of the use cases for smart manufacturing to come in the future. It is predicted that incredible things will happen in 2030 when Germany expects the fourth industrial revolution to be realized. I would like to compare the current transition from the third industrial revolution to the fourth industrial revolution to the situation where automobiles first appeared in the modern society where horse-drawn carriages traveled. Some will challenge to build an automobile. Others will say, a very talented person can make a car, so I'll make my carriage better. As we all know, carriages currently exist only in museums. In other words, there is no future for the latter. Let's compare the third industrial revolution and the fourth industrial revolution technically with respect to manufacturing systems. The third industrial revolution can be said to automate the system based on the equipment of sensors, controllers, and actuators. Then, The fourth industrial revolution will be evolved into an autonomous system that first perceives a given situation, fully understands it, and then uses artificial intelligence technology to solve problems. The digital twin-based asset administration shell technology is the first gateway to autonomous systems that will open us up to limitless technological possibilities. Hanyang University and Nestfield conducted a lot of research on asset administration shell, and I would like to introduce some of them. The first article was published in IEEE Industrial Electronics magazine on 2019. This article first conducted a survey of the state-of-the-art of asset administration shells. Second, we formalized the asset administration shell template and defined a common information model. Then, as an asset administration shell use case example, we set up an experiment with a manufacturing line. Finally, we extracted how to implement asset administration shells practically. We concluded the applications and advantages of using asset administration shells in a plant life cycle and a value chain. We also presented the best practice recommendations for different participants in the Industry 4.0 business. The second paper was also published in IEEE Industrial Electronics magazine. Here, we present a practical asset administration shell-enabled plug-and-produce implementation, demonstrating how asset administration shells communicate using standardized technologies. Compared to traditional methods, the advantages of the asset administration shell-enabled plug-and-produce solution are: 1. Asset information is well managed by its asset administration shell during runtime. 2. The communications required by the plug-and-produce strategy are conducted via the asset administration shells, ensuring reliable cooperative assets operating. And 3. The detailed asset status data including the real operation parameters are dynamically shown in a human-machine interface, greatly assisting system assessment and decision-making. The asset administration shell-based manufacturing system not only allows plug-and-produce but can also engage in order-controlled production. Based on customer orders, the decision-making layer dynamically organizes the production resources to fulfill different production tasks. The third paper was published in IEEE Access as an example of implementing the interoperability of manufacturing software using asset administration shell. This paper presents a method for implementing asset administration shells for software. That is, a manufacturing execution system, MES, combined with an enterprise resource planning, ERP, system. This method allows MES and ERP software to exchange data in real time. It is incomparably superior in time and efficiency compared to the conventional file-mediated method. Finally, an example of data exchange for manufacturing orders is presented to validate the asset management shell method. The fourth paper was also published in IEEE Access. This article presents a novel method for implementing asset administration shells and reports on the design of an asset administration shell-enabled digital solution for cyber-physical manufacturing systems. We put the proposed solution into operation in a practical plug-and-produce based testbed, which proves it can help make legacy systems become Industry 4.0 capable with minimal development efforts and updating expenses. The fifth is a paper implementing interoperability between enterprise and control applications. In this study, we provide insights into the AASX Package Explorer format and give exemplary applications on AASX. We then present an AASX-based solution for bidirectional data exchange between enterprise and control applications. This solution completes the conversion between AASX and Excel spreadsheets to enable interoperable data exchange. Finally, a data exchange scenario for motor control is constructed to validate the solution's effectiveness. The result shows no data were lost during the two-way conversions. Thank you very much for listening to my keynote speech. If you have any questions about this keynote speech, please send an email to shahong@hanyang.ac.kr.